Okay, I'm going to go over this question from this particular homework set. That's 2.3 is the section. It's called properties of functions, I think. And the very last problem, number 13, it's about finding the volume of a box when you can vary how tall the box is going to be by how deeply you cut this little square out of the corner of the flat piece of cardboard. So it doesn't have, we got that problem from a different source, so it doesn't have any helps that you can look up, like a link to the textbook or view an example. So I thought I'd just do an example. Okay, so this is a pretty common application where we start off with a big square of cardboard. This is how boxes are made. If you've ever been to the box store, you see how that they always have a chunk cut out of the sides there. So this original one that we have in our example here is a 15 by 18 flat piece of cardboard. And we want to fold up the edges and then have this be the bottom or the floor of the box. And then these four pieces here are the sides that fold up and become the sides or the vertical walls or whatever you want to call it, the box. So in order to be able to fold these up and have them all meet, you have to cut the corner out. So the corner can be varied in terms of how much we want to, how deep a cut we want to make there. If we made a little tiny little square on each side, well, then the floor of the box would be really big, but the sides wouldn't be very tall because you'd only have that little bit to fold up. If you made the cut deeper and made it closer to the middle, then you'd have a very tall box, but it wouldn't have a very big floor in it. So you can vary the size of a box, the dimensions of the box, and the volume will also vary depending on how you make those cuts. So the volume of any box, any square box that looks like this or rectangular box is going to be the area of the floor, so length times width, just like any rectangle, but then also times how tall the box is. And that's what this X value, this bit that we're going to cut out of the corner, that tells you how tall we're going to make the sides, because then we fold that up and it becomes this side over here. Okay, so I'm going to go over here to a piece, just a regular piece of paper, to kind of work out the parts to the problem. Slide this back over here. So the first thing it asks us to do is express the volume of the box. So volume of a box is always, like I said, the length times width. You just do the volume of the rectangular bottom of the box, but you have a third dimension, which is how tall is it? So we call that the height. Okay, well, that box that we looked at over there, I'm going to just do a quick sketch here. Not very good because I am not an artist, a math major. Supposed to be flat. Sorry. Anyway, let's say that this is the longer, so the length would go back here and the width would be in the front. So let's say what should we do? It doesn't matter. If we kind of look at it the way it was before, we could do the 18 inches is what it was before we cut the sides out. So, you know, there was this extra little piece of cardboard that was running back like this when it was flat, kind of like this. And we cut out this corner so we could fold this piece up. So the 18 was the original inches that it was running from the flat piece of cardboard, but then we cut out this little X chunk. Remember the picture of the flat piece? And then we were going to fold that piece up. So it was 18 inches before we started cutting. And then we cut out a chunk on this end that was X inches. And we're cutting out another, the same size, whatever we choose to cut out here, we have to make the same cut on all four corners. So it started off as 18 inches minus X minus another X. So the actual side to side, once we've cut out those two corners, is 18 minus 2 of the corners. So 18 minus 2x would be like the width or length, whatever you want to call it. Okay, we're going to do the same thing down the side. It was 15 inches before we cut out the corners, but we're going to take the 15 and we're cutting out that same X mystery length from both ends of it. So we do that twice. So we're going to remove 2 of those X lengths because we're cutting it twice. All right, so there's length and width. That's how you would get the floor of the box. And now the height of the box is exactly what you cut out here. So we cut out the corner and then, well, the corner would have been down here. We cut out the corner and then we fold it up. All right, so that is X. So no matter which part of the box you're looking at, the height is going to be the X. Okay, so length, oh, I don't care, 15 minus 2X. I'll just go length that way. Width is going to be 18 minus 2X. Since this is a rectangle, of course, these are interchangeable. It doesn't really matter which one you want to call length and width. But the height, we're going to designate that to be X. And we're calling it a variable because they're asking us lots of questions like, well, if you cut X to be this, what will the volume be? What will the volume be? So we're changing up how much we cut out of the corners in the other questions. So we're just leaving that as a variable. So then the volume for this particular system would be length times width times height. We're just going to multiply these three things together, and I'm just going to use parentheses. I'm not going to bother to simplify it. I don't think it says type a simplified answer. That'd be a pain in the rear end to work all that out, times X. All right, so we have an X, we have another X, we have a third X. Okay, so that's my volume. Volume typically has, if it's a box like this, it'll have 3 X's in it. Remember, we have cubic units for volume. That's one of the reasons why, because they look like cubes or boxes. All right, so that's the answer to our first part of the question when it says part A, the volume of the box can be expressed as a function of the length X of the side of the square cut from each corner, like I was saying. Okay, so again, show you the picture again. Remember, this was the 18 and 15. We're cutting out a little square on each corner, and the square is X, X by X by X by X. So we're cutting out this, if it's 4 inches, we're going to cut in 4 inches on this corner and cut in 4 inches on that side, do it 4 inches all the way around, and then this will come out we'll fold all 4 of the corners up. Okay, so there's our volume. Part B says, then it starts asking us to use it. It says, in the example that I have, it says, find the volume of a 4-inch square that is cut out. So what is the volume if a 4-inch square is cut out? So then you have to understand, how do I use that 4? Okay, well, they told us already that X is supposed to be the length of the side of the square cut from each corner. So this is telling me that X is 4. So that's what we're going to use. So we can think of this as a V of X, probably should have written it like a function. V of X equals, so I'm going to calculate V of 4. Basically just go through and substitute 4 for all the X's. 4. Now I can do this on my calculator, but I think I can handle it. 2 times 4 is 8. Do my order of operations, work from the inside out, do multiplication before subtraction. So that's 15 minus 8 will be 7. Over here, do the times, 8. 18 minus 8 will be 10, and then times 4. All right, now we just multiplied that, got 70 times 4, 280. Now, these were inches, right? So the units will be cubic inches. 280 cubic inches. Sometimes you'll see it written like this, 280. They'll just write the shorthand for the unit and just put a cube above it like that. That also means cubic inches. And that's how you know you're dealing with a volume value, because they measure cubics. Okay, so then they ask us again for what's the volume for a 5-inch square cutout. Now I believe as you do the problems, the dimensions on the rectangle are going to change. It might not be 15 by 18. It might be 24 by 20 or something. And then these particular values they ask you to calculate will be different, but the basic structure of the problem is the same. So the volume, the second one on my particular problem was for 5 inches, for a 5-inch cutout. Okay, so that means we're going to use X to be 5 this time. Terrible 5. So we'll do the same thing. Our original function is right here. So we'll do 15 minus 2 times 5. Work that out, times 18 minus 2 times 5. And then times 5. So every place there's an X, we put the 5. Again, I can do this in my head because 2 times 5 is 10. So 15 minus 10 would be 5. 18 minus 10 would be 8, and then times 5. All right, so depending on how you want to do that, 5 times 8 is 40, 40 times 5 is 200. You do 5 times 5 is 25, times 8, 200. Whatever it is, it's going to be 200. And will also be the same units, cubic inches. Okay. So that's how you get volume of a box when you just are starting from a flat piece of paper or flat piece of cardboard or whatever the materials are, metal, and you're wanting to form a box from a flat piece. You're going to cut the same corner out of all four sides. And then there's a couple of more questions here. It wants us to pick a graph, choose the correct graph below. Now for this, I'm going to switch over and show you the graphing calculator. So notice that they all kind of come up to a peak and then fall, but they have a little bit different shapes here. You can see I've already marked this one, but I'm going to graph it on my calculator, set my dimensions. See, they have it. They didn't tell us dimensions on how to graph it on our calculator, but if we follow, all of these have the same, well, except for this one. We'll go 0 to 9 on the x-axis. And then if it only goes up to 225, don't I already know that one of my volume outputs is higher than that at 280? So if you look at what this is a volume graph. I should say y equals v of x. So this is volume going this way. See, it says v of x there. So my volume is, I know it's higher than this one. Anyway, let me stop talking and just switch over to the graphing calculator. So let me go to that right here. Okay, there we go. Now I'm going to put that function into my calculator that we just figured out for the volume. So that was 15 minus 2x. I need it to be in the general forms with the x's in it. And my dog is wanting to eat. But we're not going to do that right now. Give me just a minute to finish this thing. And then times x one more time. So this is what we put on our homework, 15 minus 2x, length times width times height. I'm going to go set up my window. 0 to 9 is what my math lab dimensions were on all four of those graphs. So I will do that, 0 to 9. Now the y values, we've realized all of them go up to 450 except for that one that went up to 225. We decided 225 wasn't high enough because one of our values we know already goes higher than that. So we'll let it go from 0 to 450. And we graph. Okay, so it's one that starts close to the origin. It actually is on the origin. Kind of looks like a parabola for a bit, but on the other side, it kind of spreads out as it's heading down. So it's not quite symmetrical. So when we look at that one, that'll tell us which one of our graphs to pick. So let me go back to the homework. Nope, not that one. This one. All right. Is it a little light go up? No, the light's on. There we go. Anyway, so now these are the choices that I have right here. And so that's why we're picking this one. That it goes up and then it kind of spreads out as it goes downward. This one stops below 225 and the other ones, this one has kind of the slow change on the left-hand side. And the one on the far side is like is a perfectly symmetrical parabola. So this is the one that looks the closest to what we have on our graph. So that's why I picked this one. Okay, and then the one last question is really one of the useful things about why we do this kind of stuff. What values of x give the max volume for the box? This we're just going to do off our calculator where we run that max feature to find that little turning point right there where it peaks and then it starts to fall. It'll identify that point for us and we're just going to read off the x value because it says what value of x gives the maximum volume for the box. So maximum volume refers to maximum height or the y value. So somewhere close to 300, a little over 300, looks like maybe, I don't know, 300, between 300 and 350, we'll find out. And then we will, it says round to the nearest 10. All right, so let me go to the calculator one more time since we already have it graphed there. Okay, we're going to find this point right here approximately. This is one of the nice things about our graphing calculator. So we're going to run the calculation, which is over the trace key. This is how you can find estimates for all these different important points on your graph. Because it's the top of the hill, it's a maximum. So we are going to run the maximum routine that asks us some questions. Now, this is what happens when you do a max. It says, hey, what's the left bound? If you go down here, it'll tell you what to do. So left bound means show me a point or type in an x value that represents a point that is left to the left of the point you're interested in finding. So the point I'm interested in finding is this peak right here. Right now the cursor is on the right. I could either type in an X value down here like 1 or 2, those are definitely to the left of that, or I could just use the arrow keys and just visually move the cursor until it's past that peak. So it doesn't matter if you type in a number or if you just move it manually with the arrows. But I can tell for sure it's to the left of that turning point, and that's what it's asking me to mark. So I'm going to hit enter, and then it's going to say, show me something to the right. What is the right bound? So now I'm going to go and do the same thing, slide it back over, where again, I can type in 4 or 5, to just jump it over there, but that's clearly past the peak on the right. And so what it's trying to do, all you're doing on these routines is you're just marking a section of some graph and asking the calculator to run through all those points and spit out the highest one. That's why you want to make sure that you've got the right interval here so that the point you're looking for is in there. All right, now when it says a guess, that would just be in case there's more than one point that looks like they're the same height. You want to find one first or the other. It doesn't really matter, so I'm going to skip that and just hit enter again. Okay, so it thinks for a minute now. It's found the best estimate it can based on the window settings and the function and everything. So it says this maximum occurs at approximately X value 2.716, Y value approximately 326.6077. Okay, so that's approximately the maximum. The Y value is the maximum. So when we say maximum, we mean maximum Y value, maximum function value, or in this case, maximum volume, 326.6 cubic inches. That's the most that we can cram into this box from an 18 by 15 piece of flat cardboard. If we want the maximum volume, we need to cut the corners out to be about 2.7 inches on each of those squares. And then when we fold it up, that'll be a height of 2.7, and that for some reason is the maximum, 326.6. So I believe the homework asked it to round the X value to the nearest tenth, so 2.7. Okay, so that's how we would finish that problem. So what value of X gives the maximum volume for the box? We put this on our calculator, ran the max function, marked it on the left and the right side, had it find the max for us, and it said the X value for that was about 2.7 inches. Okay, so that's the rest of it right here. So the max volume occurs when X is approximately 2.7 inches. And we did that by, on the calculator, we did a graph. That's terrible. We found that on the calculator, and it was about 2.7 by, what was it, 3 something. Anyway, 326 or something. Now I have to know, hang on a second, 326.6. Okay, so the maximum volume, it didn't ask this, but it might on another question, because this is pretty common. The max volume is the Y value, 326.6 cubic inches, just if anybody wants to know. Okay, so that's number 13. That's the logic behind all those questions that it's asking you. So hopefully that will help you get through that last problem. Have a great rest of your day. Bye.